Hello and welcome to Submodule 2.3. This is the third module on AC analysis. In this module, we're going to go over several quantities that relate to AC power. And we're also going to recall the theorem of maximum power transfer and use that concept to understand how to correct the power factor in AC circuits. First, let's look at instantaneous power in AC circuits. If we have a voltage and a current with the following equations, as we have seen before, given by a magnitude and a frequency and some phase angle, and also of course a current with a magnitude, a frequency, and a phase angle for the current, we know that the instantaneous power is the product of the voltage times the current. So if we just formulate that expression, we have this over here. And using the trigonometric identity shown here, cosine A times cosine B is equal to half the quantity of cosine A minus B plus cosine A plus B, we get that the instantaneous power expression is equal to the amplitude of the voltage times the amplitude of the current divided by 2 times the cosine of the voltage phase minus the current phase plus the cosine of 2 times the frequency, the angular frequency in this case, which is 2 pi f, times time, plus both phase angles. What this shows is that since the phase angles are constant, this term is a constant. So in terms of a time varying signal, the instantaneous power expression has 2 times the frequency of the voltage or the current signals. Now let's look at average power. For any periodic signal, the average over time is given as the integral of the signal over time over any period t divided by the period. So as we apply that to the expression that we just found for P of t, we get this expression here for the average power. Now, since the time varying signal is a sinusoid, the average is going to be 0 over a full period. That leaves us with the constant term, which is 1/2 the amplitude of the voltage times the amplitude of the current times the cosine of the difference of the voltage phase angle minus the current phase angle. Of course, it is good to highlight at this point that for a purely resistive circuit in which the current and the voltage are in phase and therefore the difference in their phase angles is 0, then the power will be 1/2 the amplitude of the voltage times the amplitude of the current. At this point, I would like to recall the maximum power transfer theorem that says that for any source that is modeled by the Thevenin theorem with some source voltage through some Thevenin impedance driving a load impedance, the maximum power is going to be transferred from the source to the load when the load impedance is the same as the Thevenin impedance. We're going to use that concept to correct power factor, and we're going to define that in the slides ahead. We're going to use that concept to correct for the power factor and make our AC circuits more power efficient. Now let's define and calculate the effective or RMS values involved in AC power. We can say that the power is equal to the effective current square times some resistance, where the effective current is equal to the square root of the integration over a period of the time varying signal of the current, that integral divided by the period. Therefore, we can say that the power is equal to 1 over the period times the integration over a period of the current square, the time varying signal, times the resistance over time. That current is also the RMS current. So we can say that the power in an AC circuit is equal to the RMS voltage, the root mean square voltage, times the root mean square current times the cosine of the difference of the phase angles between the voltage and the current. Of course, again, if the circuit is purely resistive, then this cosine term will be 1, and we have that the power for the resistive circuit is simply the RMS current squared times the resistance, or the voltage, the RMS voltage squared divided by the resistor. And I would like to go back to the previous slide and highlight that this I effective is also called the RMS current. We are calculating the root mean square of the current by integrating the square time signal over a full period, any time interval that represents a period, dividing by the period, and then taking the square root of that quantity. Now let's define power factor. Power factor, if we go back to our power expression that we had derived in previous slides, power as the RMS value of the voltage times the RMS value of the current times the cosine of the difference between the voltage phase angle and the current phase angle. The power factor is defined as the ratio of the power divided by the product of the RMS values of the voltage and the current. Therefore, the cosine of the difference between the phase angle of the voltage and the phase angle of the current is defined as the power factor. And we call the difference between those two angles the theta of the load impedance. The other question of interest is what we will call complex power, which is given by the root mean square of the complex voltage times the complex conjugate of the RMS value of the complex current. That expands in polar coordinates as the magnitude of the voltage at its angle times the magnitude of the current at minus its angle, or the magnitudes multiplied together at an angle that is given by the difference between the phase angle of the voltage and the phase angle of the current. This is a complex quantity, therefore it's going to have a real part, which we're going to call the real power, and it's going to have an imaginary part, which we're going to call Q. And we can see then that the tangent of the difference between the phase angle and the voltage and the phase angle of the current is equal to Q over P, Q, which is the reactive power, and P, which is called the real power. And these are depictions of these quantities in the complex plane. If we have some current vector at an angle of theta I, and we have some voltage vector at a voltage of theta V, all reference from 0 from the real axis. We see that the difference, this over here, this angle is the difference theta V minus theta I. Therefore, the projection of the current onto the voltage vector is going to be the magnitude of the current times the cosine of theta V minus theta I, and the other component of this vector orthogonal to the voltage vector is going to be the magnitude of the current times the sine of the difference between theta V and theta I. The real power that does work for us in AC circuit is going to be these two components, the voltage and the projection of the current onto that vector. And that is the real power that we are interested in, the one where the current and the voltage are in phase. In this figure, we see the complex power with its real projection with an angle of theta V minus theta I, and we see the other projections for the reactive power of plus Q or minus Q, depending on whether the complex power is on the fourth quadrant or in the first quadrant. Now let's look a closer look at that complex power in the first quadrant. We see that the complex power here is the magnitude of the current times the impedance. That's another way of writing that complex power, where we have with an angle of theta V minus theta I, that projection is going to be the real power, which is going to be the magnitude of the current times the real component of the impedance. And then we have the reactive power, which is going to be the magnitude of the current square times the imaginary part of the impedance load. So the question is, if we want our power to be as close to a real power as possible, we want to minimize the reactive power, as it is in industrial loads where we can have a large component of reactive power because of the coil windings of motors, for example. We want to make this component smaller so that most of the power that we are delivering, the total or complex power, is closer to the real power that is doing actual work. If we want to minimize this reactive power, we have to correct for the power factor, which is the difference between the angle of the real power and the complex power. In other words, we want to reduce this angle, the difference between the voltage and the current angle. We're going to do that by putting a capacitor, what we call a shunt capacitor, between these two lines. That's going to have the effect. Remember that the capacitive impedance is in the negative imaginary direction. If we add the capacitive load, we're going to reduce the total imaginary load such that the reactive power is reduced and the power that we deliver, the total complex power that we deliver, is closer to the real power that does work in our load. So we can say that the all power before correcting the power factor is equal to the real all power plus some all reactive power. Again, that also can be written as some all complex power magnitude at some all angle. And what we need to calculate is what is this new capacitive load that we need to put to reduce the angle. Of course, the new complex power is going to be the old real power. We want to leave that one alone, but we're going to have a new reactive power that is going to be smaller. And that's going to give us a new complex power that is going to be closer to the old real power. That's going to have a new angle for the complex power that is going to be smaller than the old angle. So let's look at the steps to do this. That new power, that new complex power, is going to be the old complex power plus some new power due to a capacitor that we're going to add. It's going to be in the minus Q direction. So we're going to have the new real power plus the new Q, the new reactive power, minus the old real power plus the old reactive power. We're going to calculate the power due to that capacitor that we're going to add as the difference between the new complex power and the old complex power that we had. So if we write the new complex power as the new real power plus the new reactive power minus the old real power plus the old reactive power, this simplifies, and remember that the new real power and the old real power are the same. We want to keep that the same, so we get that the difference between these two quantities is the power that we want due to that capacitor that we're going to insert. And we also know that the complex power is equal to the voltage square divided by the complex conjugate of the impedance, where that impedance, since we know it's a capacitor, is minus 1 divided by j omega c. So we have the new complex power equals to the power in the capacitor equals to minus j omega c times the RMS voltage square. And with that, we can calculate the value of the capacitor that we would put in a shunt configuration between the source and the load. So pictorially, this is the effect that that capacitor is going to have. Originally, we had a complex power at some angle, at some old power factor, with some reactive power, large reactive power that we want to reduce. We add a capacitor in the minus j direction that is going to combine with the old reactive power and is going to reduce that angle. So now we have a new complex power that is closer to the real power that does the work, a smaller power factor, and a more efficient circuit. So in this submodule, we looked at the calculation of different figures related to power in steady state AC circuits, and we looked at the power factor correction as a technique to reduce the reactive power and make the delivered complex power closer to the real power that does the work in AC circuits.